let us continue with exercise 45. So here we are in a dihedral group Dn, and R is this rotation through an angle 360 degree divided by n. That means R is a symmetry of the n-sided regular polygon, and F is any reflection. Then depending on the value of n, we have been asked to simplify these products either in this form or this form. So the thing we should note that will be of use in the solution is this. For any n, one can see that FRF is equal to R inverse. Irrespective of the value of n, this relation is true. That means it is true in any Dn. Okay, now in part A we have this product f r to the power minus 2 f r to the power 5. Now using elementary group theoretic properties, this part can be written like this. That is, f r to the power minus 2 f can be written like that. We will write a justification for this step, but let us now use this relation. So here we have R inverse to the power minus 2 times R to the power 5, and that is equal to this, which is R to the power 7. Since n here is 4, so this will be equal to R cube, because R to the power 4 is identity, and that is because R is a rotation through an angle 360 degree divided by 4. So if you perform it 4 times, then that will give you a complete revolution. So your figure of that n-sided regular polygon, it will come back to the actual same position. So that's why that equals the identity rotation through an angle 0 degree. So R7 becomes R3 or R cube. Now here we write, note that for any two elements A, B in a group, and any integer m, we have this identity. We have used this identity in the first step, or we can end the calculation here and write it as a new line. So here f r to the power minus 2 is also an integer, because here m can be negative. F, since f is a reflection, f is its own inverse, so this is equal to and that in turn is equal to okay, so this is the justification. Now we are going to use this relation as well as that technique again in parts B and C. So in part B what we have r to the power minus 3 f r to the power 4 f r to the power minus 2. Okay, so here we have that thing in the middle where we can use this identity with 4 in place of m. So we can write f r f whole to the power 4 r to the power minus 2. So this gives us minus 9. Now here the value of n is 5. So n is 5 means what? R to the power 10 is equal to identity. R to the power 5 is also identity, but so is R to the power 10. So that's why you can write because this becomes identity. Now use one of the rules of exponent that gives you r. So here the simple answer is r. And finally we have f r So in part C we have f r to the power 5 f r to the power minus 2 f. So here we apply this identity in the beginning itself and write this. This becomes equal to okay. Now in part C n is 6. So here you can write okay, because n is 6, so you can write r to the power 6 minus 7, or you can also write r to the power 12, square of r to the power 6. So using the rule of exponent here you get this. So the in part A and part B the final answer is in the form r to the power I, whereas in part C it's of the form r to the power I times f. Next, (46) prove that the set of all rational numbers of the form (3 to the power m times 6 to the power n), where m and n are integers, is a group under multiplication. Multiplication means multiplication of rational numbers. Okay. For integers m1, m2, n1, n2, we have, the first thing we need to verify is that this set is closed under multiplication. So that's what we are going to show. Because of commutativity of multiplication, we can write this product like this. Commutativity as well as the fact that multiplication is associative. Which by the rules of exponent, that is already available for real numbers, equals this n1 plus n2. Since m1 plus m2 and n1 plus n2 are integers, the number belongs to the given set. So given set is closed under multiplication. Okay, so we have verified the first law, the first axiom, closure property. multiplication of rational numbers is associative. So in particular, for this type of numbers also, multiplication will continue to be associative. The number 1, which is equal to 3 to the power 0 times 6 to the power 0, acts as an identity element, because that is the identity element with respect to multiplication or for the operation of multiplication, and it happens to be expressible in this form, that is the given form. So 1 belongs to our set. And finally, the number 3 to the power minus m1, 6 to the power minus n1 in the given set acts as an inverse of this number. So the given set is a group under multiplication. Let me put some ink first and then we will continue. Next, exercise 47. Prove that if G is a group with the property that the square of any element is the identity, then G is abelian. Okay, so let A and B be any elements in G, then AB is equal to AB whole square, because we could have started like this. A times AB times B is equal to A square B square. If you just take the A's together and the B's together, you get this. But it is given that the square of any element is the identity. So this is equal to E, B square is also equal to E. But again, AB whole square is also E, because AB is also an element of G, and that gives us AB or A times BA B. Thus, by the cancellation laws, you can cancel A from both sides using the left cancellation law, and using the right one you can cancel B from both sides, and you will have AB equal to BA. So that means any two elements in the group commute. So that's why the group is abelian. Then 48. Prove that the set of all 3 by 3 matrices with real entries of this form: 1A B 0 1 C 0 0 1. That is, in the language of matrix theory, these are upper triangular matrices where the entries in the below the leading diagonal are all 0, and all the diagonal entries are equal to 1, is a group. under matrix multiplication. These matrices are related to quantum mechanics, specifically the Heisenberg's uncertainty principle, named after the Nobel laureate Werner Heisenberg. So they form a group. We have to prove that under matrix multiplication. So let A1, A2, B1, B2, C1, C2 be real numbers. Then the product of these two matrices this will also be an upper triangular matrix. If you know the result from matrix theory, if you take the product of two upper triangular matrices, then the result is again an upper triangular matrix, which however now we are going to actually calculate and verify in this 3 by 3 case. This in general is true for any two n by n upper triangular matrices. So this is equal to 1 plus 0 plus 0. So 1. A2 plus A1 plus 0. That means A1 plus A2. B2 plus A1 C2 plus B1 plus B2 plus A1 C2. 0 plus 0 plus 0. 0 plus 1 plus 0. And 0 plus C2 plus C1. That means C1 plus C2. And the third row, 0 plus 0 plus 0. 0. 0 plus 0 plus 0. 0. 0 plus 0 plus 1. So this is again a matrix of that form where these are real numbers. I hope I have calculated it correctly. Let me just see once more. The lower triangular part is okay. What about this one? This is the first row, second column. So that means A2 plus A1 plus 0. So A1 plus A2, fine. First row, third column. B2 plus A1 C2. Okay, B2 plus A1 C2 plus B1. Okay, and this one, that means second row, third column. So 0 plus C2 plus C1. Yes, fine. So the given set of matrices is closed under matrix multiplication. Frankly speaking, I have no idea how these things are useful in quantum physics and how it's related to the Heisenberg uncertainty principle, but it would be very interesting to see how. Maybe at some time I will be able to see if I get time. Okay, so this is closed. Now next, this one you can verify also if you want that matrix multiplication is commutative associative in the case of 3 by 3 matrices, but we are just going to assume that. We know that multiplication of matrices is associative. In fact, this fact is not true only for, is true not only for square matrices but matrices of any order. Say A is an m by n matrix, B is an n by p matrix, and C is a p by q matrix, where m, n, p, q, these are some positive integers. Then you can form this product. Now if you form A, B, and then take the product of that with C, then it becomes equal to this product, and this can be proved in general, and the proof is also not extremely difficult. You just have to figure out what the product ultimately will be. That's all, on both sides, and it will be equal. The 3 by 3 identity matrix that is this one, where these 1 and zeros, these are real numbers, is of the given form, because we see the form requires that the entries below the leading diagonal be all 0. The entries above the leading diagonal can be any real numbers, and those on the leading diagonal must be equal to 1. Belongs to the given set of matrices and acts as an identity element. We already know it's a pretty straightforward fact that if you multiply any matrix, any 3 by 3 real matrix with the identity matrix in any order, that is, if your other matrix is A, then you can perform identity times A or A times identity, you are going to get A. So this acts as an identity element. Next, the matrix. Okay, let us write the matrix here. 1 minus A, AC. Okay, we have taken A1, A2, so let's consider the inverse of the first one. A1, C1 minus B1, 0, 1 minus C1, 0, 0, 1. in the given set of matrices acts as an inverse of this. To verify this, you just have to calculate the two products and see that both of them are equal to this. In fact, let us quickly just see that. We are not going to make that a calculation a part of the solution, but for our own sake, let's just verify that. It's been raining for some days, so the humidity level is quite high. That's why it's difficult to clean the board properly. Okay, so if you calculate this product, say 1 minus a1 c1 minus b1, 0 1 minus c1 0 0 1, and 1 a1 b1 0 1 c1 0 0 1. What do I get? 1 plus 0 plus 0 1. a1 minus a1 plus 0 0. b1 minus a1 c1 plus a1 c1, that minus a1 c1 plus a1 c1, they cancel out, and we already have b1, and with that we have minus b1, so everything cancels out with something else and we have 0. Then in the next row, 0 plus 1 plus 0. What? I think I made a mistake. 0 plus 0 plus 0, yeah, second row, first column. So 0 plus 1 plus 0 1, 0 plus c1 minus c1 0. In the third row, 0 plus 0 plus 0 0. Then in the second column, 0 plus 0 plus 0, and finally 0 plus 0 plus 1 times 1 is 1. Yes. And what about the other product? One plus 0 plus 0 1, minus a1 plus a1 plus 0 0, a1 c1 minus b1, minus a1 c1 plus b1, so 0, 0 plus 0 plus 0 0, 0 plus 1 plus 0 1, 0 plus minus c1 plus c1 0, 0 0 0 0, 0 0 0 0, and finally 0 0 1. Yes, so this indeed is, it acts as an inverse, and it also belongs to the set of matrices that we are considering. So that's why the given set is a group. under matrix multiplication. Then 49. Prove the assertion made in example 20 that the set of all positive integers less than the positive integer n is a group under multiplication modulo n if and only if n is a prime. Okay. So if n is a prime number, then this will be a group under this operation, and if it's a group under this operation, then n has to be a prime number. So we have to prove both the things. So let us first assume that n is prime. Now for any two numbers in the given set, we know that if we calculate the remainder when we divide the product AB by n, then the remainder is a non-negative integer less than n. We know that the remainder is written like this, right? AB mod n. This is the remainder when we divide AB by n, and according to the definition of multiplication modulo n, if that is our operation, then if you operate A and B using that operation, this is the answer. This is a non-negative integer strictly less than n. Okay. Our aim is to prove, you see, you have all the positive integers less than n here. Our aim is to now prove that this number cannot be equal to 0, because then it will belong to this set, and our binary operation will be closed, or in other words, the set will be closed under the binary operation. So suppose AB mod n is equal to 0. That means the remainder that you obtain when you divide AB by n, that remainder is 0. In other words, it means that AB is divisible by n. Then n divides AB. Now we use the assumption that n is a prime number. since n is prime, we have either n dividing A or n dividing B. Okay. However, this is not possible because A and B are both positive integers strictly less than n. And we know that when n is a prime, this type of integers are relatively prime to n. They are not divisible by n. So our supposition is wrong, and hence AB mod n should belong to this set. So that means this set is closed under multiplication modulo n. Now we are going to use the fact that this operation is associative. Okay, we are not going to demonstrate that here, we are just simply going to mention it. One can prove this quite easily. We know that multiplication modulo n is an associative operation. The element 1 in this set clearly acts as an identity because it already acts as an identity for ordinary multiplication. So in particular for multiplication modulo n also it acts as an identity. If you calculate this, and if you calculate this, you are going to get the same remainders because these numbers themselves are same. Or for that matter, if you calculate a1 mod n, all of these are equal. Okay, now next we come to the question of existence of inverses for the elements. So let I be some element in this, since I is relatively prime to n, and this is happening because n is, or we can in fact include that also. Yeah, why suppress the information? Let's just write everything. Since n is prime, we have n cannot divide I, and hence n and I are relatively prime. So there exists integers alpha and beta such that alpha I plus beta n is equal to 1. Then okay, now what I am going to conclude from here is this. If we divide alpha I by n, then the remainder is going to be equal to 1. Why? Because you see, alpha I is equal to minus beta times n plus 1. Okay, so that means alpha I has been written in this form where we have some integer times n plus 1, where this 1 is greater than or equal to 0 and less than n, less than the divisor. And why is 1 strictly less than n? Because we have assumed initially that n is a prime number. So because of that, n is greater than 1. So this 1 qualifies as the remainder, and that because of that, minus beta qualifies as the quotient in the division of alpha I by n. So that means alpha I mod n is equal to 1. Okay, and this tells us that alpha acts as the inverse of I, but actually that is not quite true, because this integer alpha is not necessarily in this set. The integer itself is not necessarily in this set, but we can rectify the situation by considering alpha mod n, that is the remainder when we divide alpha by alpha itself by n. With that, if you multiply I and then find mod n, then also because of properties of this modular multiplication, this will be equal to this. So let's just argue like that. Then this part I am not going to make a part of the solution. Then I am directly writing mod alpha I is, oh sorry, what actually, alpha I mod n is equal to 1, which implies alpha mod n I mod n mod n equal to, or we can write one more step because we need to multiply this with I. Okay, this mod n is equal to alpha mod n times I mod n. Because I is coming from this set, so if you divide I by n, the remainder will be I itself, and that's why I mod n is equal to I. If you are confused about this calculation, then you go back to the previous chapter, in the beginning chapter where I think we are in the beginning chapter, in the preliminaries. You go to the first section and there you will come across exercises that show that this type of calculations are valid. So this mod n, and from that some exercise that we encountered there, this is equal to nothing but alpha I mod n, and this is equal to 1 because of this. So now note that this number alpha mod n is actually a number here, and at the same time multiplying that with I modulo n, our calculation is not ordinary multiplication but multiplication modulo n, has given us 1, that is the identity element in this. But there is still one more problem. How are we concluding that alpha mod n is not equal to 0? That is happening because if alpha mod n is equal to 0, that means alpha is divisible by n, but then beta n is also divisible by n, so 1 should be divisible by n, which is not possible because n is a prime number, so it cannot divide 1. So for that we write like this. Note that alpha mod n is not equal to 0 since otherwise n divides alpha and alpha I plus beta n equal to 1 would then imply this, which is clearly not true. So alpha mod n does belong to this set. Thus alpha mod n acts as an inverse of I. So we have verified all the group axioms now. Hence this is a group under multiplication modulo n. but this is only one half. In the other half, we have to prove that if this is a group under multiplication modulo n, then n has to be a prime number. Instead of proving that, we will prove the contrapositive, namely that if n is not a prime number, then this cannot be a group. I think in this context, n has to be greater than 1. I am not sure, nothing has been mentioned here, or maybe because I have not actually gone through the text part and I am directly solving the problems. I have missed, maybe I have missed the fact that in this context n has to be greater than 1. However, if n is equal to 1, then what happens? If n is equal to 1, note that the way this set has been written, it is supposed to be the set of all positive integers less than n. If n is equal to 1, then this set is empty actually, because of the presence of this n minus 1. There is no positive integer less than 1. So that's why in that case automatically it cannot be a group. So let's just argue like that. Conversely, let n be not a prime number. That does not immediately imply that n is composite. Be careful about that, because no one has said that n is greater than 1. N is not prime means it just simply that it's not prime. So either it's a not prime number that is greater than 1, or it is equal to 1, which is neither prime nor composite. If n is equal to 1, then this is the empty set which is not a group under multiplication modulo n. Every group must have some element, at least one element. So this trivial case is gone. Now that n has to be greater than 1, the fact that n is not prime will imply that it is composite. Now assume n is greater than 1. Then n is composite and so there exist integers. Okay, let us take, have we already taken a and b? I can't remember. So let us take mu and, or we can take u and v also. There exist integers u comma v such that n is equal to uv, u is greater than 1 and less than n, and v is also greater than 1 and less than n. That means compositeness of n has allowed us to factorize n non-trivially. U and V are non-trivial factors in the sense that none of them is equal to 1 and also none of them is equal to n in this factorization. Okay. Now U and V belong to our set that we are discussing about. So they belong to this set because of these inequalities. But if we calculate their product modulo n, then that is equal to n mod n, which is equal to 0, and this does not belong to our set. Hence this is not a group under multiplication modulo n. So this now finally completes the solution. That is, we have proved that if n is not a prime number, then this set is not a group under that operation. Or equivalently, if it is a group under the operation, then n must be a prime number. Okay. Then exercise 50, and in exercise 50 there is a mistake in the statement of the exercise. In a finite group, show that the number of non-identity elements non-identity elements that satisfy the equation element to the power 5 equal to identity is a multiple of 4. Is a multiple of 4 actually. In the text it's given 5. It's not a multiple of 5. If the stipulation that the group be finite is omitted, or is omitted. What can you say? about the number of non-identity elements that satisfy the same equation. Okay, so first of all we have to show that in any finite group the number of non-identity elements x for which x to the power 5 is equal to identity is a multiple of 4. That number will definitely be finite since the group itself is finite. We have to prove that the number is divisible by 4. And if we remove this stipulation finiteness from this situation, then what can you say about that number? Okay. Now you may be wondering why 4, because in the text it's given as 5 and I am saying that it should be 4. For that you just look at this group. Set 5 of all the integers from 0 to 4 under addition modulo 5. We already know that under addition modulo 5 this is a group. And how many non-identity elements are present here? 4. And all of them satisfy this equation. Because in this group, this equation means what? Adding an element 5 times. So this gives us, but we have to keep in mind that the addition is addition modulo 5. So the ultimate result has to be divided by 5 and then the remainder will be the answer. So this is equal to 0 and you can pretty much see that if you do the same with 2, 3 and 4, you are again going to get 0. So in this group this number is not 5, it's actually equal to 4. So that's why the original question is wrong. It has to be 4. Okay, now we are not given just Z5 or Z5, we are given a general finite group. So the solution can be obtained like this. Let x be a non-identity element in the group. The finite group is there in the background, we are not naming it, we are not giving it any name, that satisfy this equation. Let x be one such non-identity element. Now we are going to make a supposition and we will show that the supposition is wrong by way of contradiction. Suppose there exists an integer I such that I is greater than 1 and less than 5. That means I is either 2 or 3 or 4 and x to the power I is equal to e. Suppose. So that means we are supposing that either x square is equal to e or x cube is equal to e or x to the power 4 is equal to e in our original group. Since, now note that the value of I is either 2 or 3 or 4 and in each case it is relatively prime to 5 because 5 is a prime and these are positive integers less than 5. So since GCD of I and 5 is equal to 1, you know pretty well what I am going to write, that a linear combination of I and 5 will be equal to 1. So there exist integers, say alpha and beta, such that I alpha plus 5 beta is equal to 1. Then x is equal to x to the power 1. In place of 1 we can write I alpha plus 5 beta. Now you use the rules of exponent that is available in any group to write this element like this. This is equal to 1 because of our identity, and this is also equal to identity because x satisfies this equation. And this is a contradiction because x is assumed to be a non-identity element. So our supposition is wrong. That is, x square, x cube and x to the power 4 are all non-identity elements. What more is true, just like x, they also satisfy this equation. Note that okay, but before which one should I write first? Should I first write that they satisfy the equation and then write that they are distinct, or should I first write this? Okay, let's just write about the equation. Note that x square to the power 5, by the rule of exponent, this can also be written as x5 whole square e. Same thing for the other two powers. And x to the power 4 whole to the power 5 is equal to x to the 5th power whole to the power 4. So they again satisfy this equation. Moreover, x square, x cube and x to the power 4 are all distinct. Do you realize where is this distinctness coming from? Suppose they are not distinct, then just I am giving you an example. Say x is equal to x square. Let's see that first. Then from the cancellation law that we have in the group, we will have x equal to identity. This is a contradiction because x is a non-identity element, so x cannot be equal to x square. Okay, if x is equal to x cube, then again by cancellation you have x square equal to identity. But we have already proved that x square cannot be equal to identity. For no integer I in this range can x to the power I be equal to identity. So this also cannot be true. Similarly, if you assume x is equal to x to the power 4, then x cube will be identity, which again would violate that thing which we proved. And you will get same thing, I mean similar things, similar contradictory conclusions if you assume say x square is equal to x cube, or x square equal to x to the power 4, or x cube equal to x to the power 4. So I am not showing all those things. You can pretty much understand how they are distinct. So what have we now achieved? We have achieved this. If x is a non-identity element in the group that satisfies this equation, then there are 3 more non-identity solutions to that same equation. So each non-identity element, or in other words, each non-identity solution to the given equation produces 3 distinct, 3 other solutions. So that means the non-identity solutions are coming in a set of 4 solutions. Okay. So each non-identity element x that satisfies this produces three more non-identity solutions. Now the thing that is left for us to see is that, say you have got these solutions in the group and all of them are non-identity. Now if you get another new solution y which is not anywhere here, then for that non-identity solution also, I mean at the same time y is also not equal to identity, for that one also you will get solutions like this, which are again all distinct among themselves and all of them are different from the identity. Now what we are trying to see is that these 2 sets will be disjoint. The way we have chosen y already is not here. Okay, so y is not equal to any of these elements. That's how we chose y. Is it possible for y square to be equal to some element here? If y square is equal to x, say, then what do we get? Can we get a contradiction? If y square is equal to x, okay, then y to the power 4 is equal to x square, but we know that y to the power 5 is identity, so that means y to the power 4 is y inverse, okay. So that means what? Y then has to be equal to x to the power minus 2, and since x to the power 5 is equal to identity, so x to the power minus 2 is x cube, and this is a contradiction because according to our choice y is not here in this set. Similarly, if y cube is here, but this we only considered, okay. I think we have to argue all these things because they are quite different from one another. So let us now do this. Why we need this extra step? It's because, fine, we are getting solutions in a set of 4 distinct group elements, but if we get another 4 distinct group elements which are also solutions to the original equation and there is intersection, then together they will not give me 8 solutions, 8 different solutions, but they may give me say 7 or 6 depending on how the sets are intersecting. But if they are not intersecting, then apart from these 4 solutions I will then again get 8. In this way, if every new set I am getting does not intersect with the previous solutions, then I will get 4 more. So this way I will get only multiples of 4. Now let y be a non-identity element in the group such that if there is no such y, then fine, we have got all the solutions. Like in case of the group Z5, there we have only 4 non-identity solutions, but if there are more, then that is the case we are considering. Now let y be a non-identity element in the group such that y to the power 5 equal to e and y does not belong to these. We claim let's write our claim in a new line. We'll take some space. Actually, this whole thing can be proved quite easily and in one line using Lagrange's theorem, but that so far has not appeared, so we cannot use that. We have to do all the calculations. Suppose y square belongs to this. that is contrary to our claim. We are now supposing that this is a common element. If y square is equal to x, then y to the power 4 is equal to x square. This implies y inverse is equal to x to the power minus, oh no, sorry, y inverse is y to the power 4, so this is x square, and this implies y is equal to x to the power minus 2. Okay, I should not get distracted. And since x to the power 5 is equal to identity, so this is equal to x cube, a contradiction. A contradiction to the choice of y, that y is not here, but here we are seeing that y belongs to the set. Okay, if y square, I hope we will be able to get through this series of calculations. If y square is equal to x square, then on the left hand side we keep on doing what we are doing, what we have done here. Then on the right hand side we let it evolve. Y to the power 4 equal to x to the power 4, and this implies maybe there is a much shorter way of solving this problem, but I can think of this only for now. If you find a shorter solution, please let me know. This implies y is equal to x to the power minus 4, which is nothing but x, because x to the power 5 is identity, again a contradiction. If y square is, oh no, we are dealing with y, no? Now we are dealing with y square. Okay, if y square equal to x cube, then y to the power 4 is x to the power 6, which is already equal to x. This implies y inverse is equal to x, or y equal to x inverse, and x inverse is equal to x to the power 4. X to the power 4 is present here, so that is a contradiction to this. So our supposition is wrong. Okay, this part I leave to you. We have supposed that y square belongs to this, and in each case we have seen that we get a contradiction. Just like that, if you suppose that y cube belongs to this set, there also in each case they will get a contradiction, and the same will be the case with y to the power 4. So here we just simply mention this. However, you are supposed to complete. One can similarly show that y cube and y to the power 4 also do not belong to this set. Hence the claim. This claim along with what we proved earlier in the solution, that non-identity solutions to the equation occur in a set of 4 distinct elements, implies that the number of non-identity, okay, we can write elements, that satisfy the equation what have we written. This claim along with what we proved earlier in the solution implies that the number of non-identity elements that satisfy the equation is a multiple of 4, and that's what we wanted to show. Oh, this here, okay. The solution is not over yet. We have also been asked to say something about the same situation if the group is not finite. So for that, consider the infinite Cartesian product So if you form such a Cartesian product where the number of sets you are considering is infinite, then the elements in such a Cartesian product are sequences A, B, etc. Infinite sequences of elements in Z5. That is, all these coordinates of this sequence or this infinity tuple, if you want to call it so, are coming from Z5. Or okay, to show them more properly, let's write A1, A2, etc. such that AI belongs to Z5 for all I greater than or equal to 1. Let us give it a single name also, G, say. For any two such elements in G we define this. We define their sum to be this sequence where in A1 plus B1, A2 plus B2 and so on, the operation plus is addition modulo 5. Okay, so and it makes sense also because this A1, A2, B1, B2, these are all elements from Z5. So they are being added using addition modulo 5. So that this result again will be an element in Z5 and hence this will again be in G, a sequence of elements of Z5. Now you can clearly see that although, okay, the first thing to note here is that with respect to this operation, G is actually a group. That is the first observation. But before that observation, we need ink. It's quite easy, straightforward to show that G forms a group under this class. One can easily show that G is a group under the operation class defined above. Closure property we have almost seen. Associativity will follow from the fact that addition modulo 5 is associative in C5, because you see, although you are having sequences, you are adding sequences, but component wise in each component or each coordinate the calculation is happening in only Z5. So all the properties of Z5 will be imbibed by G. The identity element is the one where we have 0, 0, 0, all the terms of the sequence are 0, and the inverse of any such element is obtained by taking the inverses of the individual terms in Z5. That's all. Okay. Note that this group G is infinite and the elements, these elements 1 0 0 etc 0 1 0 0 0 1 and so on. That is, these are the elements which are sequences where exactly one term is non-zero and that term is equal to 1. We are just shifting that term along the sequence. First we make it the first term, then we make it the second term, then we make it the third term. If you keep on doing like this, you can clearly see that you will get infinitely many elements in G. All satisfy the equation x to the power 5 equal to e. In our group, in this group G, x to the power 5 means x plus x plus x plus x plus x, and e is the identity element, that is the sequence all of whose terms are equal to 0. So you can see that the 0 terms, when we were adding this any of these elements with itself 5 times, the 0 coordinates do not affect anything. Only the coordinate that contains 1, there you get this, and in Z5 this is equal to 0, so then you get the identity element of G. So here the number of solutions which are, and note that none of these are equal to identity. So these are all non-identity solutions to this equation. That number is infinite. Okay, so it's not even finite. Next, there are 4 more. We will finish it. Exercise 51. List the 6 elements in the general linear group of 2 by 2 matrices where the entries are coming from Z2. Show that, and the operation is of course matrix multiplication. Show that this group is non-abelian by finding 2 elements that do not commute. So the entries of the 2 by 2 matrices that we are going to consider, they are coming from Z2. So each entry can either be 0 or 1. But we have to also keep in mind that the matrices should be non-singular. They should have non-zero determinant, each one of them. The 6 elements in this are The first choice is of course the identity matrix. Then we can bring another one, okay. So these are the 6 elements in the given general linear group. Have we covered all the elements? We won't have anything else. Now we cannot take a 1 here because then the determinant will be 0, and in each of these matrices the determinant is non-zero. In this case, I mean for the first 3 matrices the determinant is 1, and for these are all, I mean for the last 3 matrices also they are 1. Actually they are equal to -1, but in Z2 -1 is equal to 1. Okay. Now this is non-abelian because say if we take the product of this matrix with this one, then what is the product? 0 plus 0, 0, 1 plus 0, 1, 0 plus 1, 1, 1 plus 0, 1. Whereas if we change the order and calculate this product, then we have 0 plus 1, 1. Yes, so they are equal. In the first row, first column elements, they don't match, so they are unequal. So 0 plus 1 is 1, 0 plus 1 is again 1, 1 plus 0 is 1, and 0 plus 0, 0. So you can see, if you know about these things, that this is an elementary matrix which is obtained by interchanging the rows of the identity matrix. You bring the first row in place of the second row, and you bring the second row to the position of the first row. Now if you multiply this matrix by this elementary matrix, then the same type of elementary operation will be performed on this matrix. What happens when you multiply from the right side is that the columns are interchanged. You see the 1, 1 column has gone and become the second column, and the second column has become the first column. However, if you multiply from the left, then the rows get interchanged. 1, 1 now becomes the first row, and 1, 0 has become the second row. So that's why these two matrices are not equal, and this proves that GL2 Z2 is not abelian. Elementary matrices are they come up when you study about elementary row operations in the context of solving systems of linear equations. Okay, what is 52? let G be equal to again a 2 by 2 real matrix, but here all the entries are equal and that single real number is non-zero. Show that G is a group under matrix multiplication. Explain why each element of G has an inverse even though the matrices have zero determinant. Yes, this is slightly peculiar. The matrices, I mean, they are just they are singular matrices. For each one of them, the determinant is 0, and we are dealing with matrix multiplication. But still, we are saying that these matrices form a group. So let us first see that they form a group. Then we will answer this: why inverses exist although the matrices are singular, that is, they have zero determinant. For any two non-zero real numbers A and B, we have 2AB. 2AB is also a real number and it is also non-zero, because if you multiply two non-zero real numbers, you get a non-zero real number. And if you now, multiply the corresponding matrices in G that are coming for the numbers A and B, what do you get? You get AB plus AB, 2AB, and you continue to get 2AB because all the rows here are same, all the columns here are same. So G, that means this matrix, because it's also of that form and where the entry 2AB is non-zero. So this matrix belongs to G, that means this product belongs to G. So G is closed under matrix multiplication. And we already know that multiplication of matrices is associative. Okay, but now what will you do about identity element? Normally when we have matrix multiplication, the identity element turns out to be the identity matrix. But now you cannot take the identity matrix because all the entries have to be equal. Note that you consider this matrix, all of these entries are 1/2. And if you calculate this product, what do you get? A by 2 plus A by 2, that is equal to A, and all the other entries also will be equal to A. So very mysteriously this matrix acts as an identity for this type of matrices. It's not actually the identity for all the matrices, but in this restricted set of matrices this acts as the identity. And the same is true if you change the order. Because here also A by 2 plus A by 2. So this particular exercise shows that if matrices and their multiplication are involved, then it's not necessary that the identity always has to be the identity matrix. It can be something else also. So acts as an identity element. Next, if you are considering this matrix, that we want to say that this matrix has an inverse, then the fact that this matrix is in G tells us that A is a non-zero real number. So that means this matrix makes sense you can in fact divide by A. 1/4A, this is also a real number and this is also not equal to 0, and so this matrix belongs to G such that if you take the product of this one and this one, then you get what? 1/4 plus 1/4, because A and A they will cancel out and you get 1/2, 1/2. Don't make the mistake of trying to bring the identity matrix here, because that is not the identity now. And thus acts as an inverse Thus, G is a group under matrix multiplication. Okay, now comes the question of how are non-singular matrices having inverses. A matrix belonging to G has the inverse in the sense that their product in any order, that is either this times this or this times this, gives us the identity and not the identity matrix so in spite of being singular, this has an inverse in G, and this inverse in G is not the actual ordinary inverse of the matrix, which however does not exist because the matrix is singular. Inverse in G, that is the important thing. Okay, two more. These last two exercises are about the definition of a group itself. Suppose that in the definition of a group, G, the condition that there exists an element E with the property AE equal to EA equal to A for all A in G is replaced by just AE equal to A for all A in G. So say we have all the axioms of group intact except for the third one, which says that there is an element E for which these three things, that is these relations, should be true, that is these three things should be equal for all A in G. Say we change this axiom and instead we relax the situation and demand that only this should be true for all A in G. Then EA must also be equal to A. If you assume this equation for all A, then EA being equal to A is actually a consequence. So in the definition there is really no need to say this as well. It's enough to show that there is a right inverse. That is, if you multiply an element from the right by such an element, you get the original element back. If there is a right inverse, that is also a left inverse and hence a two-sided inverse. Oh, we need to write the conclusion. Show that EA is also equal to A for all A in G. Thus, a one-sided identity is a two-sided identity. Keep in mind that we haven't done anything with the axiom of inverses. For every element there is a two-sided inverse, namely an element A inverse such that A inverse and A inverse A are both equal to identity, but this identity now is an element that satisfies only this equation. Okay, then we have to prove that the other thing is also true, and in fact the system is a group. Note one more thing carefully, that because we have changed the third axiom, the system G with the binary operation and with these axioms now is not a group. I mean, we don't know whether it's a group, it's just a system that satisfies these axioms. So in the solution you cannot use any result from group theory that we have seen so far. The solution to this one and the next exercise also are just some clever calculations, that's all. So let A belonging to G be any element. We already know from this assumption that AE is equal to A, but we need to show that EA is also equal to A. So let us call this element EA B. Let's give it a name B, say. We want to show that B is equal to E. Then what about AA inverse? A inverse is equal to E, because the fourth axiom is there fully, it's there with us. So A inverse is equal to E, and E can be written as E. And we are allowed to write this because in place of A you can take E, so that will give you E equal to E. Okay. Now in place of this E, you write E A inverse, because A inverse is still equal to E. And now you use the associative law, which however is available to us, keep that in mind. The second axiom is intact. Now EA is what? B. EA is equal to B because that's what we are calling it, A inverse. Okay. So now we want to show that B is equal to A. After performing this calculation, one is prone to make a very common mistake. They may start cancelling A inverse from both sides, but that cancellation now is not available to us. Why? Because our system is not a group. I mean, we have tweaked with the third axiom, we have changed it, and the system has changed. We don't know that it's a group, so the cancellation laws are not available. So we have to do something else after this. Now A is equal to AE. This is still permissible. I can write A equal to AE. Okay. Now in place of E, I can write A inverse A. Note that just like A inverse is equal to E, A inverse A is also equal to E, because the fourth axiom, the axiom that says that inverses exist, that is fully there with us. We haven't done anything to that. Then we use the okay, so after we write A inverse A, then we use the associative law to write the product like this. Now our previous calculation tells us that A inverse is equal to BA inverse. So BA inverse A. Again you use the associative law. And the fourth axiom gives us BE, and we are allowed to write BE equal to B. So that's how we get A is equal to B. Hence EA, which is B, is also equal to A. And finally another such, where now we are going to change the fourth axiom. Now we keep the third one intact. So this is exercise 54. This is the last one. Suppose that in the definition of a group G, the condition that for each element A in G, there exists an element B in G with the property that AB equal to BA equal to E. Now this E is a two-sided identity which now we have is replaced by the condition that we have only AB equal to E. Show that BA is also equal to E. Thus, a one-sided inverse is a two-sided inverse. Box have entered. So here also the beginning is the same. Let A in G be any element. Okay. Let B belong to G such that AB is equal to E. Our new axiom 4 tells us that such a B exists for A. Let C denote the element BA. We need to show that C is also equal to B. There also exists by our axiom, new axiom 4, an element D belonging to G such that BD is equal to E. You can call B a right inverse of A. Every element has a right inverse. So B itself also has a right inverse, which we are calling D. Okay. Then B is equal to BE and E is AB. Use the associative law and write it as BA times B, but BA is C, so this is equal to CB. So B happens to be equal to CB. So this implies C is equal to CE. Now in place of E you can write BD. And then use the associative law to write CBD. So that becomes equal to, but we have already seen that CB is equal to B. So this is BD and BD again is equal to E. thus BA is also equal to E, just like AB is E, BA is E. So B is not only a right inverse of A, but it's also a left inverse of A. In other words, it's the inverse of, it's an inverse element. So this completes this set of exercises. In the next video, we will move on to the next set of exercises. If you are new to this channel, please consider subscribing if you find these things helpful, that is. So that will be all for tonight. This is me, Lucifer, from a mathematical room. Have a nice night.